What is the real-life application of an asymptote? In this video, we'll examine how a horizontal asymptote helps us to determine the long-term behavior of a function. This is enrichment example 8. The concentration C in milligrams of a certain medicine in a patient's bloodstream is given by the rational function C equals t plus 4 over 5t squared plus 2, where t is the time in hours since the first dose of the medicine. So C is the concentration of the drug in milligrams, and t is the time in hours. With that in mind, let's answer a few questions. Part A, how many milligrams of the drug were initially administered to the patient? So the key word here is initially. Initially means at the beginning of the dose or at time 0. So I want to figure out the concentration when t is equal to 0. So we're going to plug 0 in for t everywhere we see a t in that function. And this gives us a numerator of 4, a denominator of 2, which of course reduces to 2. This is the concentration of the drug in the bloodstream in milligrams. So at the beginning of the dose, the patient was given 2 milligrams of the drug. Part B, find the equation of the horizontal asymptote. As you know, we determine the location of the horizontal asymptote by examining the relative degrees of the numerator and the denominator. Notice the degree of the numerator is 1 and the degree of the denominator is 2. So the degree of the denominator is bigger. That is, it's bigger on the bottom. Remember, this is the Bobo case. Bigger on bottom. The equation of the horizontal asymptote then is y equals 0. So what does this mean relative to the real-life situation, this patient receiving medicine? Well, to help us answer that question, let's take a look at the graph. Use your calculator to graph the function. We're going to use the window x min equals 0, x max equals 4, x scale is 1, y min 0, y max 3, y scale 1. And then we'll sketch the graph in the space below. So let's jump over to our calculator and go to our y equals function. And let's type in the original function. Now, the original function used the variable t. For our calculator, we're going to replace the t with an x. And we'll just remember the horizontal axis represents time. Now, to execute the specifications on example C, we're going to go to our window button and type in those parameters. So x minimum is 0, x maximum is 4, and x scale, which gives us the scale on the grid on the x-axis, is going to be 1. So every tick mark on the x-axis represents 1. Y minimum is going to be 0, y maximum 3, and the scale on the y-axis is also equal to 1. So every tick mark on the y-axis will represent 1. And then we'll hit graph. So remember, our horizontal axis is the t-axis, so we're looking at time along this axis, and we're looking at the concentration in milligrams on our vertical axis. So by looking at the graph, we can make a rough sketch by hand. So I'm going to label my horizontal axis T, my vertical axis C. So along our horizontal axis, we have hours, and along our vertical axis, we have milligrams. So on the x-axis, our scale is 1. We went from 1 to 4 hours. And on the y-axis, our scale is 1. We went from 1 milligram to 3 milligrams. Again, just sketching just the basic idea of the graph. It does something like this. Okay, with this graph in mind, let's see if we can answer the next question. What happens to the concentration of the drug in the patient's bloodstream as T increases? Now remember, as T increases, we're working this direction. So what we notice, as T increases, my concentration decreases. At the very beginning, it bumps up just a little bit, and then it decreases. Then it's going to level out above that t-axis. Now don't forget, we discovered there's a horizontal asymptote on the t-axis with equation y equals 0. So with all of this in mind, we can answer the question. as time increases, the concentration increases slightly and then decreases toward zero. So what we understand is that the milligrams increase in the bloodstream very temporarily and briefly, and then as the body metabolizes that medicine, the level in the bloodstream decreases, approaching zero over time. The next question says, at what time is the concentration the highest? Well, we want to know what's the value of this little bump right here. We don't have a way of calculating that at this point in our study of math other than using our calculator. So on your calculator, you have a button where you can calculate a maximum of a function or a minimum of a function. So we're going to type second and then the trace, or that calculate button. And notice option number 4 there is maximum. So I want to calculate what's called a local maximum. Now it's going to ask me a couple of questions. First, what's the left bound? So I'm just going to use my left arrow key to get anywhere to the left of that maximum point. So if I keep going, I want to get to the left of that maximum. So I'll just choose x equals 0 and then press enter. And then it's going to ask me what's the right bound. So I'm going to choose any point to the right and press enter. And then for its calculations, it needs a starting point. So it's asking me for a guess. Looks like that's the highest point, and I'm going to press enter. And then it calculates the maximum for us. So if we look carefully, it looks like our maximum would be, let's just go here, 0.05, and y equals 2.01. So the maximum t value is 0.05, and then our concentration is 2.01. So at what time is the concentration the highest? We can say the concentration is the highest at 0.05 hours after administration. So what you can see from this example is that the horizontal asymptote describes the long-term behavior of the medicine in the bloodstream.